I find what we're about to embark on right now an extremely intimate process, honestly. We're aiming at true honesty without the filter of trying to say, oh, but I'm smart, right? Or there's no trying to put you into it. They're just trying to ask questions. And people don't usually do that. You do that with people you're very, very, very close to. Everyone else you have a facade for in our world, right? So I really find the environment where you can just entirely wholesale abandon the facade, come in with, all right, none of us know anything. We have things we think and things we believe with different confidence intervals, and those confidence intervals are either well-informed or they're not. Right? But we're all in that situation, and only that situation. Everything we think is stuff we are imagining right now. The entire world we claim as being real around us, the physical things and so on, I'm not saying there's nothing there, but what you're saying it is coming from the translation in your brain.
Right.
It's not the same thing I'm saying it is, because my brain's translated it differently. The goal is for us to both be able to articulate what our translation is very clearly so that we can then disagree or look closer until we come to a sharper image of what we're seeing and help each other translate what it must mean so that we then see a certain reality. Right. And I mean this literally, like if you went back thousands of years, where people conceived a completely different story their whole life about what reality is. They'd never been exposed to our modern concepts of technology and communication and options and possibilities and cars. The car alone would have been enough that they wouldn't have believed you if you tried to explain what it was, right? Just the car alone.
Right.
But even if I had a magic time machine and threw you 30,000 years in the past, and you could get through the language barrier after a few years and communicate and try to convince them, no, these things really are real from the future. Even if they believed you, they wouldn't be like you are, where you have actually conceived it, the full richness of it. It cannot be taken from you, even if you never know how to get back into your time. If you spend the rest of your life in the past, it would never be removed from your mind. The conception of what a car actually is and how it plays the role or in an environment. That conception is the goal. Whether it's right or wrong, whether you can apply it now or you can apply it later, it's having access to the conceptions is this linear process through time, right? In history, people weren't dumber than us. They had a different focus than us, okay? And no one had come up with a certain way of looking at things, and no one had asked a very precise, sharp question. And when someone came along and did, the rest of humanity got to say, because it's obvious once it's pointed to. But if it's never been pointed to, it requires a first person to look.
And it's almost the same conception of when I see it, I'll believe it type of thing, right?
Yeah, but even worse. You have to see it, but you have to conceive it. The photons have to come into your eye, but then your brain has to figure out what the photons meant and put it in a story. It has to define it and judge it. It has to do all these things so your brain knows what it is. Right? It has to be a thing that was labeled in some way.
Right.
So it had to have been put into story. And here's the thing. Everything we do that with, every new observation or every regular observation, our brain is making a story, translating it, right? But the logic behind the story is the logic that your brain thinks is the logic of the universe, of reality. Obviously, your brain's not trying to lie to you. So far, your brain's working on an operating system that makes certain assumptions about reality, about what is. And it's comparing everything else to that and telling you story from the data that you see based on that, right?
Right.
So we want to really get to that foundational story. What is it? So that's where we're starting.
Beautiful.
Why would we even care? Why would you talk about what reality really is? Why are physicists even concerned, right?
Right.
Well, because this pattern of thought, where you just go about your way translating the things that happen to you, leaves you in the same story, has slightly changing details, but the story is always the same foundation, right? The things you thought about reality haven't wildly changed since you were a child. You know what I mean by that? Like, gravity seems to still be pointing down.
Okay.
Right? The things that you have observed have increased. The number of details that you've observed hopefully have increased through your life, right? But they haven't contradicted the first details you observed, right?
Okay.
The goal is to get out of the trap of thinking the same way you've always thought. So if you've first observed something and you've always observed that thing, but the first time you observed it, your brain came up with a story for that observation, it might still be using the same story, right? Because it was the first story that worked, and you needed a story. It was very useful back then, but we're talking about when you were a kid. You might still be operating on the same first assumption for how things work that you had as a kid. In fact, mostly are.
Right? So that type of, so everything, including the thoughts within our heads, have an energetic field. If you're stuck in that thought form, whether you know it or subconsciously it's still dictating your life, then to some degree you are not able to see things for how they really are. Because, for example...
But the whole point is we don't know how they really are. The whole point is, even no matter how scientific you are, there is still the debate about how you interpret the facts. Even when you don't debate the facts, there's a debate on how you interpret the facts. And conscious entities are the things that are interpreting. You either always... Well, I mean, you could just say you're always interpreting wrong. The question is, which direction of wrong? The only way you could say your interpretation is right is if it actually objectively yields the world you observe.
So guide me through this. So right now in this world that we live in, there's people that believe that the sun is rotating around the earth, right? That's just what they
That's the
see
story they have in their head.
Right,
yeah.
And that's fine. But we have now where you can get into a point where you can see beyond our earth and you can see that we are rotating the sun, right? So now that we have that knowledge, you have two people saying, hey, I can show you or tell you that the sun is not rotating on the earth. But in reality, like beyond what you think and what the other person may know, the space between that I see as the truth of the light is shining. So without light, then we wouldn't have truth.
Okay, so you're saying there's certain actions, and there's two different stories that are trying to explain those actions.
Yes,
right?
yes.
And you could argue about whether one's right or wrong, or more right or more wrong. But you're not arguing over the thing that is existing. The existence itself is still there. Yes, existence is some sort of real thing. It's physically in one state or whatever, right? But even when you have physical one states, two different people could have two different thoughts about what it means.
That's
we're not even disagreeing about what it is,
but
we disagree about what it means.
Because you could have people who are talking about, like, you know, more in Asia, like Hinduism, Buddhist terms of like yin and yang, or you could have even Christianity of the law of opposition. You know, like there is darkness and there is light. There is dark energies. There are light energies. There is consciousness. There is unconsciousness. There's two different spectrums, right? But on the physical plane,
two different ends of the spectrum. Yeah.
Yes, two different ends of the spectrum.
For any dimensions you can pick. Yeah.
But on the physical spectrum, isn't that like something that we get lost in thought form? Because that is something that, although it has an energy form.
Well, okay, so this is the point. As conscious entities, we're physical entities too, right? Mm-hmm. But as conscious entities, that means we're entities that are always telling ourselves a story about who we are. And what that story is, first element is always, what is reality? What's the stage in which I can make story, right? So reality is defined a certain way, and it might be vague. In fact, this is kind of the point where I want to go to. All of our picture about what the stage is, of where you can put story. So whatever you think in existence is, all the places you could be in existence, and all the things that could happen to you, and so on, right? That entire list of physical things exists within some sort of stage you're imagining. And that stage is what's allowing you to define yourself and everything else. But the stage itself is the contrast by which you become defined. All right. Now, since we never really talk about our assumptions of the stage, and we're all fighting over our definitions of ourself, it seems really like a futile thing. We're completely ignoring the process. You're supposed to be getting rid of this attachment to one story idea self. You can't process to a better story if you're really holding on to one, right?
It's like
Your
just
goal
identifying
is to
with it.
look at, what is it that I believe that makes me think I am this? What is it I believe that makes me think that? What is it about reality that I think reality is? And then say, well, is that a thing that I have to believe? Like, is there another option? Not because I don't like my belief. I just want to know, is this a belief that there are no other reasonable options for, and I'm picking the only good option, or am I picking one that's one of many good options? And if there are other good options, do those have other side effects that make me think I am something else?
Beautiful. That's basically questioning your thought form. Questioning what you identify with.
So whatever we personally, every individual, every conscious entity has to have some sort of conscious access to an idea of what reality is. Okay? I mean, you close your eyes and imagine deleting things from the universe. All the things you've defined and are aware of. All those properties are now gone. The earth, light, all the things you can imagine until you run out of lists. Now, whatever you think you're still imagining is your framework. How detailed do you understand that framework? Because I would venture the guess, because I just genuinely think it's true, we don't talk about it publicly. It's not part of the public persona, really. That's all background information that's extremely vague. You just imagine some sort of, I don't know, empty universe. That's not very informative. I don't even know, when I say those two words, do you have the same image in your head as me? I don't know.
That's a good point. Okay, I get you. I like that.
Okay.
I like that.
Now, here's the goal.
Okay.
Let's take away the possible judgment in this, because it's hard to listen or make progress if anyone's judging, right? Nobody on Earth has much of a better conception than that. Which means everyone who's wrestling for a definition of, look at me, how great I am, they're doing it under the confusion of, I don't even know what the universe is. Understand?
Right.
That means every person who's all proud of how, look at me, how awesome I am, has wanted us all to completely ignore the blatantly glaring, most important fact that we haven't even figured out what reality is. How am I supposed to believe you know what you are? Everyone defines who they are based in contrast to what reality is. So, okay, it's really important personally for every conscious entity to have at least the goal of sharpening their personal image of reality. Okay, so the more dialogue you have in your head, or monologue you have in your head about those details, the more specifically you can identify your comprehension of your stage, the more justification you have for any mirror image claim you can say about yourself. Instead of just vaguely thinking, well, I know I'm this, or want to be this, right? You'll have actual construction and logic and deductions and so on that you get to inform your life with. I think it's a tool humanity could really decide to incorporate in their daily practice. Say, first of all, recognize, I don't know shit, right? You don't know really anything. It's not about that you're so smart. It's about finding what you don't know, finding the biggest hole in your understanding, in the sense of, if I filled that hole, if I gained that information, it would do a lot to put all these other things together for me and benefit me in many, many conceptual, emotional ways.
Okay. Yeah. And I think I'm not huge on philosophy, but although I do love it and enjoy it, and in my life now, I like to, just every now and then, I'll be like, let's just study a little bit of philosophy. And I think it's Plato. One of the wonderful quotes he left with us was, all I know is that I know nothing. And the way that some people might read that will be like, what is he talking about? To me, it was like, for how much he did know and for how much he did see things for how they are and how they are, more importantly, I think, for how they are not, he still had enough humility to say, all together as a whole, we don't know anything, but we know enough. We have enough here that's going on that if you have enough openness, enough love and respect for yourself, that will be reciprocated to other people, and then we can actually start to figure things out for what they actually are not, and that will point to the direction of what things could be, and then eventually to things that are. That's truth, right? Past, present, future. Things that are eternally in order, really, right?
So that's cool you bring him up. He, of course, is a huge figure in history, right?
Mm-hmm.
But this idea, and of course from his predecessor, that you really know nothing as an anchor point, was also trying to point out that, hey, freedom of thought comes only from that door. If you want to be something that has freedom of thought, that's the first gate. That's always, beautiful. Every single time. If you don't step through that gate, you're not in a freedom of thought. You're parodying somebody, you're lying, whatever. If you start from, I don't know, then what you're saying is, I'm admitting to myself that even reality is confusing to me. So I am open to anything that possibly could make any more sense of the stuff I'm currently confused about.
Yeah.
And now you're stepping through an exploration of actually listening, not expecting that the next thing you hear is going to be the most important thing and true thing ever, but might be something you've never heard before that could potentially lead you to, and look this way and start paying attention to something new.
Right.
There's the goal. So he was trying to point out that, no, guys, it's not that you know something. It's not that you're proud about being one thing. You've defined your universe and therefore you. It's that you don't. It's that we don't know because our stories don't make sense. If we're honest, our stories don't explain reality. We want them to. Our best story in physics doesn't explain why we have the mass of the electron or the charge of the electron or any of the other masses or the constants in nature, but it does explain that once we have a construction with all those parameters, quantum field theory, put together in a very specific way, a geometric ensemble, think of it, okay, that it took us a long time to figure out. But once we say the reality is actually shaped a geometric way, think how much more sharp of an image that is than the vague, empty universe of some sort. Physics is saying that that emptiness thing itself has a shape, okay? It's shaped by the rules of quantum field theory. It has so many specific particular interactions and intersections that it continuously has. And once you've shaped something like that, and look at the math of the consequences that comes out of that shape, turns out you get quantum mechanics. Like all of the stuff of quantum mechanics, all the things that quantum mechanics is held responsible for doing, that shape does.
Okay.
Really interesting, right? You're
Okay.
like, well,
that's hard for my mind to follow. It's really hard for my mind to follow. But at the same time, that's what it is. We don't have all the pieces to the puzzle to say, hey, we know what it is, rather than what we are stuck in is we think this, and it comes down to theory, right?
So we can say pretty confidently, at least at the level of scientific measurement, that we know that it is geometrically shaped that way.
Okay.
So everyone's agreed that it is shaped that way. That was the big discoveries that led us all the way to that.
Okay.
The thing is, though, that ever since we've known it was shaped that way, there's still the question of, well, what does it mean shaped that way? How do I visualize this and so on, right? But ever since you've captured the math that codes how it's shaped, okay, no one's made any progress from that point on, even though we've tried. No one's made any progress at understanding why it's shaped that way. How did it get shaped that way? Like, I need some story for why that shape's special. How did it get there? Like, just knowing that it has a shape leads to more questions, right? Okay. So let's pause from that to get some more geometric stuff, because it comes from Plato.
Okay.
So Plato also noticed that, hey, if there's a shape to reality of some sort, shapes are things we can understand. Right? At least in some way, you can grasp some concepts of shapes, and they become familiar, and I can deal with shapes.
Okay.
And he realized that there are 5 simple shapes in geometry. Only 5, very importantly. You can't make any more that follow these rules. You make them out of faces, so 2-dimensional shapes, right? And then make the faces so they have all the same side lengths. So a square has 4 side lengths and so on, but then you have to make a 3-dimensional shape of the same size sides. Okay? If those are the rules, so you have to make a closed geometric shape that's 3-dimensional and all the sides are the same length. These are the only ones you can make.
What do you mean by that?
There's no more shapes that you can put together like this and close. So if you wanted it to have more sides, so a 6-sided one, you couldn't close, there would be gaps. Or a 7-sided one, or any number past that. Or there'd be overlappings. You couldn't get this to be a thing that is triangle, closed.
That is so simple, but yes. Okay.
Yes, right?
I see, okay.
But also something you wouldn't just necessarily notice until it's pointed out.
Yes.
Right? So the big thing is like, hey, but there's only 5. Why 5? That seems that there must be some special reason. And those 5 must be important for some reason, because first of all, there are 5 elementary geometric shapes. And there's only 5 of them, so the 5 important geometric shapes, he's thinking, right? And he thought, well, we got this big confusion about what shape is reality. Well, maybe reality is composed from those 5 shapes. And those are actually just the atoms of reality. And so his idea was that the tetrahedron is an atom of fire. And the octahedron is an atom of air, right? And the icosahedron is an atom of water. And the cube's an atom of earth. Okay, and the dodecahedron was an atom of ether, or think of the way the old space vision.
All the space in between.
Yeah, so the space that everything else is in. So these four are in it. So he thought they were stacked inside of each other and so on or whatever, right? But these made atoms of those things. And of course, he thought that fire, air, water, earth, and ether were the 5 things of reality at that time.
Okay.
So we don't think that now, right? Because we can explain fire and air and water and earth all in terms of atoms and so on. We have a different model now. But the point is, his genius was to imagine first to imagine how important it is that there's a list of just 5 elemental shapes. They could be important.
Right.
Because they're important geometrically. Right? So if you're trying to talk about the geometry of reality, well, maybe the 5 just important shapes of geometry are somehow important in reality. That was a really good guess. In fact, it was a brilliant guess, because if geometry has anything to do with reality, it means we can investigate it in a way we haven't been. Right?
Right.
Because geometric things you can measure, you can see their angles and sizes, you can say stuff about them.
You can see it for how it is.
Yeah, exactly.
Okay.
All right. So here, a cool thing came along. For 2,000 years, you can imagine after Plato says this.
2,000 years
for
later.
2,000 years now, people believed that the world was built from these shapes.
Uh-huh.
Now, if you believe that, like we currently believe the world's built from electrons, protons, and neutrons, you thought these were the most important things of reality, elementally, right? Then you, instead of going to church and staring at a cross for a few hours every week, you might hold one of these and try to imagine what else God's trying to tell you about reality from these shapes.
Like Egyptians would use kind of the same kind of figures, right?
Yeah, well, everyone ever since the Platonic, they became the world dominating idea, right?
Interesting. Okay,
so this is what the world believed for 2,000 years.
Okay.
Right, that's the best sharpened image we had, and it was a brilliant one because it gave us a connection to geometry, an important reason to be interested in geometry, because it connects to our understanding of consciousness and reality.
So do people now today, are they still conceptualizing this kind of concept?
Some people, yes, but that's not our scientific view anymore.
Right.
So, I mean, in the sense that we don't think reality is structured from these shapes anymore in our story. But some people do, but we consider them more like religious cult that continued on. But still, yes.
Okay. So we're, as the conversation goes further, more, you're probably going to expand on that, right?
Yes.
Where it's going. Okay.
Yes. Okay. So here's the interesting thing. These 5 shapes were studied, revered, worshipped, for 2,000 years. People wanted to know everything they could about these shapes, and yet all of those people missed something that I can show you in 10 seconds. And you'll never be able to forget. But first, before I show you, just imagine how important it was to people to understand these shapes for 2,000 years.
Right.
And no one ever figured out what Euler figured out, which I'm about to show you. He figured out that if you just count up the 0-dimensional, 1-dimensional, and 2-dimensional properties of each shape, what do you mean? Vertices, like all the points, right? So there's 1, 2, 3, 4 points. There's 4 vertices in that shape. So, we're going to label. It's got, the tetrahedron has 4 vertices. And then we go ahead and count up the number of edges, the 1-dimensional features of this shape. 1, 2, 3, 4, 5, 6. Right? And then add up the number of faces. And so on for all of them. Just list them all out. Not so hard to do. It would take you about 2 minutes. Right?
Right. Okay.
All right. And then you have a list. He noticed that if you take the number of vertices of any object and subtract its own number of edges, and then add its own number of faces, you always get 2 for all of them.
Oh, shit.
There's a simple dimensional elementary connection relating them all, and no one even noticed.
Vertices minus the edges plus the faces.
Yeah.
For all the Platonic solids equals 2.
Yeah. And remember, vertices is the 0-dimensional attribute, the dots.
0-dimensional.
And the edges is the 1-dimensional attributes, the lines. And the faces are the 2-dimensional attributes, is the faces. Right?
Okay.
So the 0-dimensional minus the 1-dimensional plus the 2-dimensional attributes equals the number 2 every time. This is considered the second most beautiful equation in all of math, by the way. In all of math. Now, of course, it's a popular bent on it. more mathematicians themselves usually pick more sophisticated things, but it is also extremely beautiful because it's elegant and simple and mind-blowing that somehow it took 2,000 years before the first person noticed. That's after people knew of these shapes, 2,000 years after we knew of these shapes and thought they were important.
Time.
Yeah.
Holy, wow. Okay.
So here's the thing. It doesn't take, that step right there, noticing that difference, is what we attribute to the brightest mind in all of our history, all of math. You could argue Euler is the smartest mind we've ever had as humans. Okay. Even more than Einstein, anyone else. He was more prolific. He came up with beautiful connections everywhere. He wrote more than any other mathematician, published more. He went blind halfway through and still continued publishing more than even before. Anyway, that level of genius is literally just the difference between staring at the shapes and the way we were before and staring at it in a meticulous way. We were like, wait a second, let me count let me measure, that difference is the difference between genius and making mind revolutionary jumps or not making any change at all.
Okay.
So it's not unreachable by anyone. It's taking a focus of, to wait, but let me measure dig into the specifics.
So what is? I'm sure you got something planned to go further into this conversation, but what did that mean? When you equals 2.
Great question. So we call this the Euler Characteristic now, and it ends up leading to an entire exploration of geometry and manifolds and all kinds of shapes for which these rules, not just the 5 Platonic solids, apply.
So he figured out something that wasn't studied furthermore on, instead of people just saying, okay, we have these 5 Platonic solids, great, they mean this, and that's like, we're going to worship this. And then he moved further into saying, hey, what does this mean? Like, couldn't there be something
not
more?
All of them just stopped and tried to worship. They tried to construct stories for how these atoms of fire and so on did things in the world. And that turned
into like religious
but they got
right?
stuck in one track of that story.
And that's a belief.
Exactly, yes.
Okay.
Yeah. But you're right, exactly.
So there was something there.
He came along without any of that belief. I don't know the exact story of how he first got introduced to these solids and so on, but I imagine he decided, because he did this all the time in all of his work, he would try to understand the concept, and then he would ask himself, before I really worry about what everybody else has been interested in these things for, what am I interested for? Right? And then that's a really powerful way to go about the world, but it's also a very rare thing to do because it requires you to be energized and motivated and so on, and following is usually much easier. It's usually 100%. Much more productive, because if someone else has already figured out the way to the top, you might as well just take their trail.
Right, okay.
Right? But he decided every time in math, you have to think about it yourself. You have to imagine what it means to you or where you're coming at it from. Otherwise, why are you wasting your time? You just want to memorize stuff so you can tell people? Yeah.
Be cool.
Yeah. So the entire history of science unfolds after basically Plato, right? Actually, it starts from Anaximander. I think we mentioned this before a long time ago when you and I talked before. But what I mean by the birth of science with him, before Anaximander, nobody had imagined there was a reason to measure distances in space or time.
Okay.
There were no clocks, of course, so what tool would you even use to do it, right, for time?
You're right.
He invented the sundial, or at least the gnome, the early version where you have a shadow cast from something, and you can then measure time. It's a very crude, but it's an actual way to measure time, right? At least over hours you're going to get a measurement.
Okay.
And that's the first measurements of time. He was the first one to come up with the idea. The whole history of humanity, like the analogy of staring at the shapes and not seeing that relationship for 2,000 years. Before even Plato, though, so before all even that story, humanity had been going about its business, hunting, gathering, mating, living, doing all of its stuff. And the thing that they occupied themselves with never brought them to a reason to be, well, let's make a ruler. Let's make a tape measure. They didn't make those tools. They've never even thought of why they would want to.
Oh, this is deep.
Yeah.
Just simple measurements.
Simple measurements. The birth of science came from one man's idea.
Oh, wow.
Who realized it's important to measure. I need to get a stick and just mark things on it and keep that damn stick and start talking about things in terms of the lengths of that stick. right? He realized that there was a reason to do that. And that when you did do that, you could also then put two sticks at 90 degrees and start talking about more and more properties. All of a sudden, you could talk about the world in a way you couldn't before.
It starts to connect the laws of the universe.
Yes.
Just by the simple stuff.
Simple. Because you now have a tool by which you invent a tool by which you go about taking some sort of measurement you never did before, paying attention to some information you never did before. You can't obviously pay attention to an object's measures in any specific way if you're not going to actually go physically measure it, right? All you can do is generally think, oh, it looks like a square to me.
Yeah, if that's the word you choose to say. Like,
yeah, exactly.
It's a square. Okay, I'm with you.
So he gave us this idea that it was possible to interface with our physical reality, the stuff that we're seeing, in a more meticulous way. You don't have to do it all the time, but before that, you couldn't do it because no one had imagined you could. Obviously, that's the first barrier to be able to do something, right? So he gave birth to science, but think of the change, the abruptness here. He invents clocks, he invents rulers, right? Or the practice of starting to measure things and stuff. And you know how much of our modern times would be different if we didn't have those two things. I don't even need to explain that, right? That's obvious at this point. But back then it wasn't obvious. Imagine he invents the first sundial and the first ruler, and he's walking the nearest town. He's not a celebrity. He's not a hero. No one even cares. No one even knows what it is.
They don't realize.
Yeah, no idea, right? It takes a long time. We were born in a world where as soon as you could see, there were clocks around, and you had to figure out what they were. And before you could talk, you knew what they were because you knew they kept ticking the whole time and they went around and around and around. That's all there is to figure out about them, right? But there was something on the wall measuring how fast time went by was a background noise of your reality. It's something nobody in humanity had ever experienced or conceived as an option before Anaximander.
Is time just a physical form that our minds have adapted
invented
to?
Or
Yeah.
Okay.
You would have
try to imagine though removing time.
Okay.
Now, what could you still describe in the universe?
Removing time. See, my mind can't really grasp that because all I know is in my mind, which is either I'm thinking, if you're thinking of the past or future, that's you still have to have a point, a spectrum of time. But I think beyond that, if energy cannot be created or destroyed, doesn't time be isn't it dissolved through that form?
I don't know. I can't quite say. I mean, even understanding how your words are being put together, but I'm trying. And this is the process, right? Every time that you talk to someone from a different field, you even have different definitions for the same words, and you think you're being very clear and technical, and you might both be, but cross talking. Okay, let me try to give it the motivation, because this is what I'm trying to tie. I'm trying to make it very clear that the scientific quest, which we've only opened up now with its first realization, right? The first idea that you can look into the world with intent and measure things and come out with a more crisp understanding of what you're seeing, right? You can start out with, first glance, make an impression, your brain immediately assumes what it is,
right?
But you don't have to stop there. That was the realization of science, the birth of science, that you could go further than just your first impression, your first guess at what the hell you thought you saw, right? Which, if we're being honest, why would you ever want to stop there anyway?
Never.
Right? Unless the first impression made absolute, complete sense of everything, which it never has for anyone.
Okay.
So why stop there? And then that's what brings me into this, let's do scare quotes, religious. There's the thing we've all kind of let fall behind. I mean, if you think of yourself as religious today, you could reword that as being proud of not improving your perspective over time. Right? It means you've picked a story, which we all have to admit as honest adults doesn't explain reality, because no story has yet. You've picked one, though, and decided to stop with it. You stuck yourself on purpose to a story, which makes you implicitly immoral. It just does. Not in a way that we need to all attack you. It made you, for yourself, implicitly immoral. It took away your entire conscious purpose in life. To change your story to something better, moment to moment, desperately so, because if you reach an insight like Anaximander did, that can open up an entire new conception of reality that gives all kinds of new ways of interaction and behaving and so on, right? New options. It can literally transform the world just by understanding it differently.
Right. Right.
And,
I see what you're saying.
It not just can, it always does.
Yes.
Yeah.
Progression.
So the progression of ideas in science that's valuable for us all, and we tend to inherit them for free. If you're born into a world after clocks were invented, it's just it's a no-brainer, and you probably never even appreciate the value of having that in your life, right?
Right.
We inherit these things so everyone else gets the more benefit. So the goal should be to make it so the next generation has something better to inherit, because not only do you have something you can be proud of that you left behind, but during your climb, you started from seeing the world one way and got to know what it was like to see it in a far more clear
and to break down your barriers of, in a lot of ways, belief.
Yeah,
because
exactly.
If you believe, it's one thing to believe in something. Like I've had this conversation a lot with people with, like, whatever I believe is what I perceive. And you can flip that. Whatever you perceive is what you believe. It's depending on how much you hold strong to that thought or that identity that's within that thought. But in reality, there is what there is, and that's where it can kind of get really hard to communicate with people in this world, because if you believe so strongly in something, that's where I was kind of going back, kind of tying it back with what I was saying before, is if it's in a physical form, that seems like one part of the equation. The other part of the equation of what it is beyond thought form. That's
how
kind of
to interpret it.
Yes, but interpretation draws you back into your mindset.
Yes,
and that you can start to believe.
So you have the physical explanation we need, and then we have to worry about the conscious overlay.
Yes,
every time.
The
exactly.
connectivity of that. Okay,
and to be as honest as we can with ourselves, we have to admit that only when we have an actual coherent story that makes sense to the person who's thinking, it has to make sense to you. It can't just, oh yeah, Stephen Hawking understood that. So what? Only when you have a coherent story, which we don't have yet, okay?
Right.
Which is why I'm excited the topic we're trying to go into. Only once you have that can you really say, now I can stand on this and take off the other direction. The rest, it's just going back and forth trying to guess.
Yeah. Okay, I see what you're saying. That makes sense.
So I also want to say that I believe it's important to remind everyone that belief is a powerful tool to be used in a powerful, positive way. Mm-hmm. And all powerful tools like guns and knives and every other powerful tool you can think of also has just as much potential to be used in the wrong way. And if you're not in charge of it, it will be used the wrong way by default. You don't leave your gun loaded around your children. You need to be in charge of your gun.
Good
right?
Point. Good
so
point.
Because belief is one of the most powerful tools for progress, it's also one of the most powerful tools for destruction. So let's talk about how belief is supposed to be, the positive side of belief. Belief is a tool you're supposed to use on yourself to leverage thought. You're supposed to say, so here's a new idea I'm being exposed to. And you say, okay, it's a hard idea. I'm not going to understand it. I can already tell when I glance that I don't get the math or whatever, right? You're already intimidated. Belief is the tool that you're supposed to leverage to get you through the paper, to get you to the end of the idea. Believe it. Try your best to believe what's being said, to comprehend what's being said. Believe that it's true. Don't ever doubt it at all, because if you doubt it, you're going to stop reading it. It doesn't matter if it's true or not true. The belief is a tool to get you through the idea so you can say, cha-ching, I now have a new idea. And now I'll judge it. No, this one's wrong, but it's really interesting. I might use that later for this or whatever, right? But you now have a new idea. You gain something. Belief is supposed to take you to a new idea. Once you gain the idea, once you've seen something, like the Platonic solids, once you've done that once, added up the numbers, seen that the equation does that for real,
that made sense.
You never, ever, ever should even try to believe that again. You don't need to. You know it now.
Beautiful. But I actually like the way you describe that.
If belief is needed twice, it's already on the wrong track. You should give 100% belief to every idea you're ever exposed to so that you can try to understand it the first time. But if you do understand it, never try to believe it again. That's a waste of fucking time.
That's beautiful.
And if you don't understand it, maybe try to believe it again so you can understand. But if you haven't given it one whole belief try, don't pretend that you get to be against it.
Yeah. like we were talking outside of with Einstein's understanding of imagination is more important than knowledge, right? Mm-hmm. It's kind of beautiful in the sense that if you do hold so strong to a belief, but you're still open-minded to expand on that until you get whether you're wrong, you're open to that, or to a point where you know you are 100% right, then belief is no longer a mental concept. It is what it is. Whether you want to believe in it or not, or the other person you try to express that truth to, that's not needed, because no matter what, the truth will always, has been, will be, and remain the same, right?
Yeah.
So that's cool. That's really cool. I like the way you put that. Yeah.
Yeah.
That is a powerful force.
People should never abandon belief. I think
I
was taught in more of a
that.
scientific tradition, and somewhat maybe by body language, but it seemed to be the cultural expectation, if not also the words layered in all of our talks, that in science, you just wouldn't be taken seriously if you're someone with beliefs. It's like almost like they wanted to say that there's religious beliefs, and that's the only kind of way you can believe, right? And so we don't do beliefs. And that's just absolutely absurd. If you're conscious, you always only believe. So if we're not going to be structuring and rigidly talking about our beliefs, then we're really just gobbledygook at that point. You have to believe something, because, I mean, you have to tell yourself a story about who you are all the time. You're always telling yourself usually the same story about what reality is, right? That belief is always there. So since we have to be something full of some belief, we should get busy with trying to sharpen that belief with our new tools like measurements and stuff like that, so that we can converge on a better and better and better and eventually accurate belief. Right? That's the goal. I mean, so science has clearly helped us get closer to the truth as we go by every new measurement.
That's true.
But we want to end up with a belief that we can then say, oh, but now I know why. I know why it's this structure. We've whittled it down to, we know what it is, in the sense of we can define it mathematically. But if I were to say, now imagine that shape, we haven't given the story.
Okay, I get you. So it's just expanding. On it until we get to a point of that's beyond belief into knowing, right? To make it simple for anyone.
All right, now let's go into day one of God School as a thought experiment.
Okay.
Let's imagine you and I are students at God School, and our instructor's up there, and they're like, all right, before you graduate from this class, you need to, grant me my ridiculous setup here, okay? The point of the class is you're supposed to learn how to create a universe yourself. All right? The first step, he tells us both, is to create anything. The first step's the biggie, okay? And you're like, that kind of makes sense, because if you go from nothing, you have to go from that to something. Where do I even start with my next thought?
This is fun,
right? So that's why we go to the school, because he's going to guide us with at least what other people have tried for the next thoughts, because you might be like, I'm dead end already.
Right.
All right, well, here. Instead of being worried about creating the right universe at first, let's just see if you can figure out any universe that you could create, okay? And so right now we need to sharpen the word universe. That'll help a bit. Okay. You need an arena or a stage that has at least one persistent property. It needs to be around from more than one instant.
Right.
All right. What's the simplest thing you could imagine that can perpetuate itself?
That's in life, but everything's made of atoms, so my mind wants to go into that concept of using atoms, which is
of using atoms to try to build a universe. We want something even simpler. Let's say you want to. First of all, we're going to try to build an extremely simple universe, right? Because if you want to build it already with me and you and all these other atoms and all this other stuff in it, that's a tall order. Let's start in God School. The simplest possible universe, just one that has any persistent property. Find a way to create the simplest possible way you can think of, or even possible it is, if you can prove the easiest way,
Light.
How do you make it?
I don't know.
Okay, but your guess is that it might be the simplest thing.
Yes.
Okay, that can be a legitimate guess. There's something even more fundamental, turns out, the physicists have already figured out, than light. It's the properties, the dimensions of time, space, charge, mass, and temperature. Those 5 dimensions are present everywhere in reality, somehow.
say this again, because it's going to take me some time, because I've heard you say this before, but I want...
There's 5 dimensions that make up our physical universe. Now, it might be in our school's order that you don't have to make anything near this same thing, but in our physical universe, the best we know in physics is that it's made up of 5 measured dimensions of measure. 5 kinds of things you can measure. Everything else is just a combination of those. It could be complex combination, like 14 of these and 35 of those, but it's just a combination. Okay? So those 5 things, those 5 types of measure are time and space, the first 2, which the first scientists introduced. You already got 2 of the first 5.
Okay.
And then think how long it took from there until we start figuring out what the hell charge was and started measuring it. Like electron charge. That's the next one. And then mass. We knew of mass, but not what it was at all, right? So time, space, charge, and mass, and temperature. And those are the only 5 things that really exist as things you can measure elementary, right? Everything else is a composite. You can have you can time squared over mass cubed or whatever you want, but it has to be of those things. There's nothing else to measure that we know of.
That, what you just said, is beyond my understanding, but what you just said with those 5 things, that what makes up our world/universe, makes sense.
Okay. So in our universe, if you took everything out, took all the planets and the light and all the energy of any sort you could think of, what would still be left, the things we could still say about it, is somehow there would still be time, there would still be length, there would still be the possibility for charge, but although we've removed things with charge in this case, and possibility for mass, and temperature.
You lost me there. What do you mean?
It means in this
void, right?
No, you could not remove those 5 things.
Oh, I see. Because no matter what, whether you have,
if you take all the atoms out,
light,
space is still there. You can't take it out. And what else can't you take out? Well, if you can't take space out, you can't take time out.
Oh wow!
And there's a little caveat. You can do a very tricky thing to make a black hole where you have an actual location where there's no time happening, right? But you're not just deleting the action of time from the metric. It's just connected.
It's connected.
Yeah. So there's 5.
And we just use the word time to measure.
Yeah. We should say more broad on that. So those 5 things are all inherent, completely open mysteries.
There we go.
Okay, let's be very clear about that. We have no idea what any of those are. But we can tell you a lot of things that happen with those attributes. A lot of things they contribute to, a lot of relationships between them. But if you ask fundamentally, so what is time? What is mass? What is charge? What is temperature? What is space? There are some answers. There's people who have put together models for partial answers on those, right?
We've learned how to use
them. But what is the right answer? Well, we don't know yet. We don't know.
I've never gone to this place.
So that's the level of our fundamental confusion in physics. We don't know how to explain where those 5 attributes come from to begin with.
Right.
We have to kind of just assume they're there, and then we describe fields existing in it and how they interact, but we didn't know why they were there to begin with. In God school, you got to first make a stage that contains, well, if you want a simpler one, but it has to have at least one expression. Something you could point to and say, in this universe, we're going to call that time. It has to have one thing happening. One measure of back and forth or whatever, or repetition or cyclic.
Something that's in order.
This shape called the hyperbolic figure 8 knot, which we show here.
Hyperbolic figure 8 knot.
Defines a very important minimal possible geometry that can be formed from wave actions that are twisted against themselves and not infinite. So it's a finite amount of energy that you twist wave together. And when you twist it just right to form this shape, what you're forming is there's waves out here with some sort of exterior boundary, and everything's twisted just right so that if you're inside the toroidal region in there, by the way, the cutouts are just so you can see inside. Okay, so pretend fill it all in so there's no cutouts symmetrically and so on. And now you know what the inside looks like though. But if you were trapped inside and the fluid's doing all kinds of twisty, weird things to you, you're never going to come out here. And if you're out here, you're never going to go in there. You can go inside the funnel and around in and back out, but you're never going to find yourself inside this toroidal region. So this shape is a balance shape of inverted actions, of inverted wave actions, or just think of it as symmetric twists, okay? But this twisting emits a hierarchy of rotations, different sizes of actions. You can draw a circle around the smallest one in here, right, around the figure 8 in the middle. That's the smallest cyclic action, the smallest circle you can make. Here's another circle. That's the next cycle that this thing makes. Then you have another circle goes around this, right? Bigger in size, but they're all different sizes. So it's emitting a balance of cyclic rotations of different size.
Cyclic meaning like symbiotic? Like
cyclic, like return around. It always
so
comes
it's
back
always
around,
coming back
doing
around.
the same thing. It doesn't have to be just in a circle when you put all of them together. We're going to put 5 cycles together, and the 5 circles eventually always repeat their path.
Okay, I get you. I get you.
But this general shape is dividing the fluid into a region out here and a region in there. And the region out here is doing 3 things, and the region in there is doing this circle and that circle things. Right? 2 things.
Okay.
But the 3 things out here are exactly inverted of the actions that are happening inside. Okay, so it's all one balance.
Okay.
The reason this is cool is because in our class assignment, we might want to say, hey, all right, this is my starting point. I want to say my simple universe, the simplest one I can imagine, is just going to be this simplest hyperbolic manifold, this hyperbolic figure 8 knot. It's defined mathematically, even though it's a new concept, you can check and see it's the smallest possible way to twist hyperbolic elements together and form a closed volume element of fixed balance, okay? Since we know that geometry is there, we could then say, and in our universe now, I have 5 different sized actions that are always happening in this thing. This balance always has 5 things in it.
Okay.
And now I have a universe that has 5 dimensions in it. Fantastic. Great, because you actually do. At this point, you've now created a simple universe that has 5 dimensions, 5 unique actions that you can measure. And they're always present. Okay. Now, but does this simple universe you created, does it have any correlation with our universe? At this point, we don't care. At this point, we just wanted to create some universe that has some sort of persistent properties.
Okay.
All right, so we're still in God school.
Right.
And then we came up with this idea. We're going to present it to our teacher. You want to give it a go?
Let's go.
What you try. What do you say to him? Our task is to create a universe that has any persistent properties at all, right?
We have to have at least one thing that is going to be part of the equation of space, time, charge, mass, and temperature. So at least one.
At least the one we could at least call
to
that
start.
in our
universe. That's where we're going to start.
Yeah.
Is with one of those. That makes sense.
Yeah. But in our case, instead of just doing one, we came up with this idea, and we're a little apprehensive because we don't know if the teacher wanted us to do this or not, but hey, the smallest possible manifold shape, geometric shape that can be self-balanced against itself. You know, the action falls apart the same way that it falls together, if that makes sense. Like a vortex splits in 2 orthogonal ways, but it also comes together in another orthogonal way. Otherwise, it would just be spreading away, right? It's splitting and joining and splitting and joining and splitting and joining in perfect balance.
That's what orthogonal means?
Orthogonal means independent. You can think of it as 90 degrees, but it's more than 90 degrees. It means literally independent in every geometric way you can think of.
Okay.
So yeah, think of perpendicular, or think of it arranged, usually perpendicular. Almost always means that, but the word orthogonal points to something a little bit more than just being 90 degrees.
Okay.
It means explicitly independent dimension.
Okay.
It's a unique measure of its own.
Okay. Interesting.
Now in this case, that helps to know it doesn't have to be at 90 degrees all the time to know what I mean. It needs to be an independent measure. Here, we're bringing him, all right, we're going to bring you the simplest, because you said we just needed a simple universe. We're just going to bring you the simplest possible self-balanced manifold called the hyperbolic figure 8 knot. And it has 5 things, but you didn't say we only had to have one. You said at least one, right?
Mm-hmm.
So what do you think his response is going to be?
See what you got.
Yeah, we're going to do the same thing with the history we got here. Okay, let's be more specific about your universe. Great, you've created a universe. That's great. You've created a balance, something that's going to persist over and over and over. And when we look at that balance, so far we've only identified it to the precision of saying it has 5 parts. We didn't tell you exactly what the parts were or anything. It's like looking at a cube and noticing how many faces it has. But you didn't notice the rest, right?
Mm-hmm.
Okay, that's what we've done. Now he's going to come back and say, he or she, our professor, come back and say, Right, well, if that's the universe, then characterize that universe. If your universe is the domain within this balance, so all the way out to the furthest reach of this balance, we'll draw a boundary. Everywhere within that boundary is your universe, and your universe is dancing like this. What else can you say? What else explicitly can you describe?
That characterizes it?
Uh-huh.
Anything that's on this earth is really what...
In the universe we created, though, this is all that is this one balance, right?
Okay.
So we would have to define what light even was if we wanted it to be. If we wanted to say something in this balance is light, we'd have to point that out as an extra feature. Now, of course, we're looking at the shape and you're seeing the whiteness of it, but the shape is just showing a geometric boundary.
Okay.
That nothing crosses in this balance.
Okay. I don't know.
Yeah, so it's a big problem, actually. It was only in the 1970s, the mid-1970s, which is basically when I was born, that this was discovered. Okay, in mathematics, that's like yesterday. That's like brand new, because math is a really old field of discoveries,
right?
right?
1970s?
Mid-1970s.
So is it this the torus field that is actually going around and through the Earth? Is that part of it?
That's much more complicated than where we're at yet.
Like you're talking beyond to
I'm saying
like the universe.
This simple balance has created our baby universe.
Okay.
Our simple universe.
Okay.
And because we're learning how to make a universe, and it's the only thing we could think of.
Okay.
Wow. Two people discovered independently, apparently, roughly at the same time, that you can make the hyperbolic figure eight knot, first of all, but that it emits a hyperbolic complement, that it has a closed surface with a fixed volume in there. Okay, which means you've created a circle. If you draw a circle around the outside of this closed surface, okay, you can create a circle from hyperbolic parts. That wasn't even known. Okay, so it was really interesting. Well, Thurston, basically one of the most recent gods of geometry, he looked at this and realized it was fundamentally important. Okay, he investigated further, figured out how to say something more sharp about this hyperbolic figure eight knot balance. He decomposed the internal component in a more geometric way and showed that they could be decomposed into two regular hyperbolic tetrahedra. Very interesting, since our first discussion started with some tetrahedra. Mm-hmm. It's also interesting that there's 5 in both of these stories. But he didn't completely explicitly describe the 5 different rotations that are making the whole thing up. He geometrically, more specifically than people before him, described it, but still, it's now looking at some more features, but not the whole thing. Okay, he didn't give us a picture that allowed us to say, oh, well, just look. If you color dyed all the flow of this thing, you would have to say every place where the flow is twisting around is a vertex of action. It's some rotation point. So all these vertices need to be identified with their actions, and so everything involved, not just this vague decomposition.
Right.
If we want to completely explicitly define for our professor the properties that this thing has, we've already identified it has 5, but now we need to say what specifically 5. That's it, right? We know what 5, we can see the circles and so on sizes, we know what actions they are, but now you need to characterize them, you need to write them down geometrically.
That's what I was going to ask you next. Is that where it comes down to mathematics?
Yes.
Okay.
That's where it comes to mathematics, because mathematics is the language of relationships. Right? It characterizes relationships. So in math, you have plus and minus. You have operations that can bring you back to where you started over and over. So you can use that operation to apply to anything that's allowed to go one way, but then return. Like this book can go here and there. So I can use the math of plus and minus to describe its position now. Right? Uh-huh. But you also have other operations that are at the same time true, important. Like what? Multiplication, which also comes with its opposite, division. Well, here's a problem though. When you're thinking, I have an operation in math, is it a real thing? Is it a real tool? How am I supposed to think of it? Because at first math was just a concept that was related to the number of things and keeping track of the number of things and selling things and stuff like that, right? But you only attached it to the number of things. You didn't attach it to the idea of number. And how to manipulate numbers themselves and relationships between numbers and more complex. Like it took a long time to realize how you could use this new language style, this mathematics language of encoded relationships that are fixed and that you now know, once I have this relationship, I've already studied it in the past, I know it has these 40 interesting properties, so I'm going to keep track of it, right? Mathematics lets us do that. It lets you keep track of way more things than you ever keep track of. But more importantly, it helps you see the connections. It defines the connections between all of those things. So it's not just giving you access to more reality, it's connecting more reality. It's a double-edged, amazing tool, right?
Right.
But it feels scary to everybody because the learning environment is almost, well, it's a threatening environment now, where the people in charge need to feel like they're the smart so they can keep their job, and the people underneath are always feeling too stupid to even really engage, so they just give up.
Right.
Yeah, that's a side note. Okay, we're back in our class, and now he's given us the next task. So before the end of the semester, we then have to characterize geometrically in some sort of precise way just what those 5 actions are, so that if you gave me the 5 actions, I could then add them all together. The answer should then just be the hyperbolic figure 8 knot, right?
Hyperbolic figure 8 knot. Okay.
Yeah. So that would be the task. Now, how do you do that task? It feels like a giant, like, oh my God, I don't know where to start kind of thing. But you understand that the task is only to do just that, right? So if you did have a geometric way of describing the ways, the 5 different actions that are combined together to make this composite dance, this balanced dance, if you can separate those actions and describe them geometrically, then we can know them extremely well. We can look into the equations now and ask questions like, what about their derivatives, or how do they interact with each other? Or you can ask all kinds of questions if you've characterized something precisely. But until you've characterized it, you can't go anywhere from it, right?
So you simplify it to focus and magnify on each individual structure of what is
each individual balance,
and how
balance in this balance.
Okay.
So if you were to drop different color all throughout the balance and then watch to see which color, because all the colors are going to follow certain paths and do certain things. But certain ones, if you started somewhere, they're going to go around and come right back to where they were in just a cycle path. There will be some geodesic stable paths if you start the right place in here. So if you find where those are, there will be 5 of them. 5 kinds of them, 5 sizes. There might be many repeats of the same ones. But
Right.
Yeah.
That simplifies it.
Good. Yeah.
Okay.
So that's our job, is just to break down the geometric structure of this shape, or the balances that combine to make this shape, right? Not so hard. It's not too much harder than a sphere. If you take a sphere and you imagine you can poke in the poles, but you don't let your fingers touch in the middle, you kind of off the side, and that's almost what we got there, except for you needed to twist the figure 8 in the middle, right?
Interesting.
I mean, that's just this inside part.
Okay.
Then we have the outside that's the mirror image of the same thing. So that's be the opposite of a sphere and untwist. And actually, it might be helpful to kind of see that way. That's what we're going to end up trying to describe. How do we get this shape, right?
Right.
I'm just trying to show you the minimum decomposition of the actions happening. So there's one blue circle in here, and outside of it, surrounded by 6 more of the same size circles, but you can ignore those right now. That's balance 0, that one inner blue circle.
Okay.
So if I put some dye there, that would go around and around, come right back, come right back.
Okay.
But if you were just a little bit outside of it, you'd probably go all around, right?
Right.
That's the one stable path right there. All right, this red one here now, notice it's at 90 degrees to this one, okay? It's also different size then, and it sweeps around. So this flips, right? This one and this one are the same circle halfway around each other. Follow?
Okay, I'm following.
So this now is the internal structure here. That's this, okay? Outside of that has to be exactly inverse balanced. We have 2 balances in here, balance 0 and 1. This circle makes this circle do the same rotation speed, okay? So this one's the same too. So this one's connected to that one. This one's connected to that one, okay? But from the outside, you don't get to see the inside. You just see these 2 actions. They seem like magical miracles. Because remember, if you're in the outside fluid, you can't ever access this. You can go through it, but you're not even aware that that's available, right? It's not part of your domain. Anyway, so these actions are all just in perfect anti-symmetric balance. But if you're out here, this domain is, notice this circle's at an angle. Can you see that it's twisted a little bit?
Which one?
The purple one? is at an angle compared to the red and blue ones.
Oh yeah, okay, I do see
And
that.
down
Yeah,
here
yeah.
it's the same picture,
Like
different
where
angle.
this is in front and that's in the
Yeah.
back. Okay.
Here you can see it a little easier, right?
Oh
Purple,
yeah.
Of course, then you can measure the big circle, purple.
Okay.
But note, the point is that the purple circle is composed of, made from, the joint union of this action and that action. This arrow, that arrow, and this arrow. They join together to twist this one. So their actions are making this exist. And their actions are making those actions. So the whole balance is perfectly symmetric.
Right. So you could not have one without the other.
Yeah, they have to be there together. Great. But that's what we wanted in our system because it's a closed system and it's balanced and so on. Okay, good. But now we can also kind of pictorially, it's a cartoon because it's reduced and nothing's in motion, but we just separated this so you can see the sizes of circles, and we saw that there's really two inside, two kinds of circles we care about on the inside, and outside there's, the domain of the outside is one circle composed of two other circles on the outside.
Mm-hmm.
Cool.
Okay.
Real quick, the red one out here is going to be the mass boundary, the blue one out here is going to be the charge boundary.
So it's balance 3 and balance 2.
This one's going to be the time boundary, this one's going to be the space boundary.
Whoa.
And this one's going to be the temperature boundary.
Start that over. That's cool.
The time, you don't have to memorize it yet, we're going to get there. But this will be the time boundary, balance 0. Balance 1 is the red circle, and it's the space boundary. And it's going to work out this way for our actual universe, but in our class, in our God class, we would be describing, we just need to describe the 5 boundaries, we could label them time, space, and so on. So you wouldn't even expect from that it should be our universe still be this way. I wouldn't, but maybe you would if you realize how fundamental it is that this is the most elemental balance possible. But that's kind of, I think, an intuition that takes a while to absorb. Okay, space-time, charge, mass, temperature. And they're all connected in a scale. This one's the biggest. This is not to scale. Don't think this is to scale. It's certainly not to scale. I squished them so it's all fit in one picture. But it goes logarithmically bigger that way. Okay. But other than that, it's right. But the logarithmic difference. Okay. All right. That same picture, separating the scales of circles that are connected. I'm writing mathematically here. And all of this new notation, so nobody would understand this right away. Okay?
Yeah.
Let's make it very clear.
This is gibberish.
Balance 0, 1, 2, 3, and 4. Boundary 4 and inverse 4. Let's just first see what those mean.
Boundary 4 and inverse.
We know balance 1, we know what we're talking about there. Balance 1, 0, 1, 2, 3, and 4. That's pointing to the middles of all these actions. Great. Boundary 4 is this right here. And boundary inverse 4 is that right there.
Okay.
And they're going to be under, if this one's going that way, then this one's going that way. They're going to be doing the exact opposites of each other.
Yeah, okay. So it's like parallel.
Connected. Yep.
Okay.
So now we look at this again. Balance 0, 1, we know which two they're talking about. 2 and 3, we know that, and the 4 is the purple one. The boundaries of the 4 ones are in play with these balances. Why? Because balance 4 is the reference frame. So it's the one we assume doesn't move. So its boundaries are motion, not its center. Okay?
Wait. And does it matter that my mind is thinking of that as temperature?
This is right. It is the temperature zone. So this is it turns out this reference is not just a reference of one in the temperature domain, it's the reference of one for all of them. All of them agree that this is the one. They only agree that that is the one.
It's like just the order.
They define the one. These guys, this system says, in this system there'll be one projected scale in which things aren't fucked up. Every other scale, things are doing weird shit. There'll be one scale that's projected as the stable scale. That scale is the reference scale. That scale is 1 second, the 1 meter, the 1 kilogram, the 1 coulomb, the 1 Kelvin. All of those agree on the same scale.
Whoa.
Yeah.
Whoa.
Really cool.
Really
Because they all project the same one. So in our hyperbolic figure 8 knot dance, all 5 of these things are combined together, but that combination only has one scaled projection that seems like this is the normal scale, nothing's really fucked up here.
Okay.
Right?
Okay.
If you go way bigger than that, then the horizon's changing. If you go smaller than that, things are really zipping around doing 2 different weird things. Right?
Okay.
All right, so we've got the 5 balances. We know how they're connecting. Just 0, 1, 2, 3, and 4. So 0, 1 on the inside, 2, 3, and 4 on the outside. But 4 is composed of 2 and 3. Right? And its boundaries are the ones that are balanced with these other balances.
Okay.
Great.
Okay.
Now, to describe what those balances are, this is our most general description. Not specific yet. General is there's going to be an interaction. We're going to call this one interaction 0, because it's balance 0. So the first one there. and an outer action, outer rotation. And there's going to be a number of hinges or partitions that this is talking about, that it's rotating over.
Okay.
What do I mean by inner and outer action? The circle, of course, is the balance line of balance 0. So that blue circle is literally the line that the die would be balanced on. If you stepped a little bit outside of it, you wouldn't follow that circle. You'd go off and do other things. If you go a little in, you'd be off.
Okay.
So that balance line has a different description of its inside and its outside. Its inside can be doing complicated balance against itself, but the outside has to be a smooth rotation countering that balance. So this balance line has an inside description and an outside description. Cool, it's a circle, so that's great. So that's how we're breaking these apart. In each case, there's going to be an inside and outside.
Okay.
Now, to make all of these seem simpler, the outer rotations, I just said, have to be just a smooth rotation, countering whatever's happening inside.
Okay.
So we can change all of those to just call them e to the something. I'll call e to the something 0 and 1 and 2 and 3, right, to keep it in sync. So some outer rotation. E to the something means in math that you're rotating. So if you did e to the pi I, that means you flipped all the way around to there. You rotated 180 degrees.
Wow. Okay.
Yeah, so it's just a way to show you magnitude of rotation. Okay. So this is just a prescription now for asking, if I knew the interactions, then I could solve for the outer rotation that balanced that interaction to keep this symmetry.
Okay.
Cool.
Okay.
Now, it's not important that you understand any numbers yet. So far, we're just talking about how we're composing our balances.
Yeah.
Right?
It makes sense. Okay.
Now, we could, from this structure, we could fill in all the rotations, the e's. Cool. That's more detailed. We still have nothing about our interactions detailed yet. But first, before we do that, let's do all the hinges, all the derangements. A derangement, the symbol for derangement is the exclamation point before the object, so before the n.
Derangement, what do you mean by that?
Yeah, exactly. Good question. Before I talk about derangements, let's write a little bit about factorial. So a factorial would be this, and by n I mean you can use any number, 1, 2, 3, 4, 5, but they have to be these whole numbers, not negative. Because this function is only defined to work on the whole numbers actually. Okay, but it's not cut in between. Factorial means if I had 5 factorial, that equals 5 times 4 times 3 times 2 times 1.
Oh, wow.
Means you take the number and you decompose it into all of its possible...
You break it down.
Smaller parts. Break it down to all of its smaller parts and see what its total composite of smaller parts is.
Interesting.
Yeah, great. And it turns out to be a useful feature that I would never thought of if I hadn't been introduced to, but it leverages things that you can ask about reality that are connected under this partition relationship or so on, right? There's relationships in reality that relate to this, so it becomes a useful feature.
Okay.
Well, if we put the exclamation point on the other side, before I do that, we can connect this function, this definition. This is how you do if you see this, if you see exclamation point afterwards, it just means take all the whole number jumps down.
Okay.
Well, you can extend that guy to what we call the gamma function, okay? You can say the gamma of n, but the gamma n is basically just n minus 1 and then factorial has it. However, it's also defined between all the whole numbers, so it's defined everywhere. So the gamma function is even more useful because it has a continuous definition everywhere. But it's still just talking about, it's not important you can know all this, it's not that critical.
Okay.
But it's still just talking about balancings and partitionings.
Okay.
It's a math function that encodes something important about balanced partitions.
Interesting.
The derangement is just, it's connected to this, but it wants to know if you have 5 things. So if I put 5 in for n, you can put any number you want for n, but if we put 5, then I want to know how many ways can you rearrange those 5 things? First question. Next question is, how many of those ways involved everybody moving? Nobody got to hold still in those rearrangements. That's what a derangement is. So all the rearrangements that required everyone to move some. So nobody gets to hold still, everyone's an active player, right, in the rearranging. And if the rearranging is available under motion, then it's a derangement that counts.
Okay.
So the derangements available to 5 objects, or 5 different rotations, is 44. That's just a math fact, right? It's always going to be 44, as long as this is 5.
Okay.
Cool. The only reason that I went through all that is so that at the end you would see that there's a connection. So if you remember, we had an understanding for what the 44 came from.
Yes.
It relates to our base derangements of our 5 actions.
Okay.
Cool. That's all you need at this point to know what it's going to do for us. So since we know we're defining this thing from the very beginning with our 5 balances, that was the most blatant first step, right? So we're going to be specific and say, of all the derangements available to those 5 rotations, all of them here at the very bottom, the balance is going to be all concentrated there. We have one rotation, an outer rotation, and an inner action. The inner action has to be simple and elegantly, if this is the simplest possible balance, and we're now talking about the simplest or the smallest action of the simplest possible balance, which is composed of 5 actions, the smallest one of them should be, I don't know, if I was playing God School, I'd pick a circle. Seems like the simplest thing, right, to jump to.
Right.
So you can define that equation, pi r squared. I know you've seen that one before.
Okay.
This equation for the area of a circle.
Okay.
Times by our outer rotation. So we're saying literally our equation is the simplest equation you could make in math about this balance. The full bottom derangement structure is equal just to a circle being balanced by an outer rotation.
Okay.
Really awesome.
Interesting.
No real big gaps of, okay, you want me to believe what? So far, I'm asking you to believe the simplest thing I can imagine.
Right.
All right. Now I'd say, well, okay, but I can't solve for this variable you put in here. Imagine it being an x or whatever, right? This phi naught. I can't solve for what that is because I don't know what r is. I know what pi is, I know what squared is, I know what e is, I know what equals and exclamation n is, right? I know what all that, but I have 2 things I don't know. If I knew what r was, I could solve for that one. If I knew what this was, I could solve for r. But we know what r is. R, the radius of the circle, is hyperbolic. So we can put in the equation for the hyperbolic sign for our radius. So now we modify this circle with a hyperbolic radius. Really awesome. You might not remember this one, but cosines and sines, these are the cousins of cosines and sines, hyperbolic sines and hyperbolic cosines. Okay, they're the inversions of circles, basically. When you set r equal to the hyperbolic sign, and you put its argument, what the action of the hyperbolic sign is doing, is splitting in 2 orthogonal ways, 2 90-degree ways. So you put 1/2 squared as its argument. Then we get this equation. Pi this squared times by that rotation equals our derangements at the bottom, okay, for balance 0. Now everything's in here, we can solve for our rotation. We can find out how much rotation balances against this action, this minimum possible action in our balance. Cool,
This is insane.
Yeah, but it's also easy, right? It's just a circle and a rotation. There's no like, okay, now we're going to import this crazy new math idea. No, it's the simplest, oldest math ideas.
Right.
All right, so let's solve. When we do, ask the computer, we get this number, which probably means nothing to us, but we can keep track of it, okay, just in case. Because in our baby universe here, the simplest one we can define, we've now done something more explicit. We can tell you what the smallest action, that cycle, what its outer rotation is. Specifically, I can tell you to any digit I want, because 44.0000000, all these other numbers we know infinitely, right? So we now know that number to any digit we want. Fantastic. Especially when you know that it connects to anything. If it didn't connect, you just say, well, it's because it's the smallest boundary condition of our baby universe. And we're proud because we're able to explicitly define it, and now we know a little bit more about our universe. That's cool.
The fact that I've seen this in your book, so this is no one else has grasped.
This is all entirely new. We're going to get the whole story together eventually, but so far we're just in God school.
Okay.
So far we're just saying our only task isn't to define our universe, it's to define a universe, anyone we can come up with. So we picked the path that, well, let's pick the simplest possible one. We look up in math for a while and we go, okay, hey, did you know there's a simplest possible manifold definable? Like Plato found these 5 simple shapes. There's more like a 3-dimensional wave shape. You can close a surface boundary, right? But if you ask all the things that can do that, say, what's the simplest? Just give me mathematically the simplest possible one that's been defined, right? Well, let's pick that as our universe then, because it's simple, and let's talk about it. We've so far noticed interesting things that it's got 5 unique properties, and we've characterized the smallest of the 5, one of the 5.
Right.
But to jump to why it's so exciting, so that all the listeners can also be really excited, because it's hard to see math as we're talking, right?
Yes, it is.
This simple equation allowed us to characterize or define the value of the external rotation keeping that balance, right? So we can now say something we couldn't say about this minimal boundary, the smallest action in this minimal stage. Why do we care? Because it turns out in reality, the Planck time, which we've measured as the mysterious limit of time, the smallest measure you can make in time, not technologically right now.
That's what we call it.
But it's the limit ever we can come to, called Planck time. The guy's name Max Planck, but in America we say Planck.
Okay.
At least I do.
Okay.
Okay, so it's a mystery. It's a huge mystery in physics. So we've found that there's a minimum cutoff in time. Wait, what? Why wouldn't it be 0? It needs to be 0. Anything not other than 0 doesn't make any sense at all. We have no story for why there would be a minimum cutoff. And yet, we've measured one as being this. We've measured it well. It's exactly known to be 5.391247 plus or minus 60 in the 47. That's how well we know this, times 10 to the negative 44 seconds. That's our scientifically known number, right?
That doesn't make sense to me, but that's interesting.
Interesting. Here's more interesting. The minimum boundary condition we just defined for our minimum balance stage happened to have an external rotation of 5.391258 within the error bars, and we know all the rest of the digits, times 10 to the negative 44. The minimum cutoff of time is the same geometric number as our minimum boundary balance in our hyperbolic figure-8 knots.
Holy fuck.
Yeah. Coincidence? Maybe you could think that's a coincidence. It's a lot of digits to rationally think. I mean, 2 digits, I'd still think coincidence. 3, 4, I'm starting to say there's something going on. Yeah. We've gone past that, right? But you still could. You can be like, I don't know how to interpret that, so let's shelve it. Cool. Where we're going with it, though, as we characterize all the rest of those 4 actions remaining, we got 5 total, we did 1, we do the same exact thing in every case. There's a Planck length, a minimum unknown reason for why, cutoff in space. There's a maximum cutoff of charge, mass, and temperature in reality. We've measured them to these accuracy in each case, right? But we don't know why they're there. And we've got one geometry that gives us those as the only options for the boundaries. It's a dead ringer, honestly. It's an obvious thing that needs to know, like, okay, we're going this way. But so this is the point. When we characterize, and we just mathematically broke down the first one, you saw it wasn't too complicated.
Right.
People aren't really, if they haven't done math in a while, either something being a rotation you might have to look up again, or equation for a circle, but still.
I would need an hour, good couple hours just to sit and just go through that. But
everyone should. If you find something that tells you anything potentially matched with some mystery we've never explained before, you should be staring at that shit for hours until it really absorbs. You know?
When you put in the action that's on top of the thought form, that's when you start to understand. Yeah, it solidifies it 100%.
Yeah, just like teaching does too.
Yeah.
You can teach it the way you think it. But teaching out loud, you get to hear yourself say it, which is actually a new experience. Usually you're hearing in your own head.
Right.
So that's helpful, but it's also helpful to see whether or not what you just said made sense to someone else. Not necessarily that they already had the same background information as you. Maybe you're not expecting it to make sense to them. But it's nice to know which parts don't, because those are things you can, it gives you another bridge. Or they might have a question that you'd never come to before because of that,
Exactly. That's true. You can help edify each other.
Yeah.
Okay.
All right, so I feel like I'm going to run out of energy soon. Let's wrap up a little bit. In our God 100%. Class here, we've now presented to our professor a minimal geometric balance, the hyperbolic figure-8 knot, and we said this is our universe that we're presenting, or that we've created. But then we found so far that when we characterize first, there's 5 actions in this thing, and we like that because ultimately we wanted to characterize a universe that had 5 things in it, 5 dimensions, right? And we could call them the same thing, whatever, try to make it close. But first you need some persistent presence, some sort of thing that's perpetually there, okay? We've got all 5, we've got the right number of things to begin with, that's cool. Biggest next feather in the cap is that when we characterized the first one and broke it down, found out what the external rotation was, that defines a boundary condition of the first minimal action that happens to perfectly match the boundary condition of time in our physical universe. Mind-blowing. Really mind-blowing, because this is saying, if it's right, that we now have characterized the geometric boundary of time. We didn't even know there really was one before. We kind of suspected from general relativity. I mean, in a sense, we can characterize a boundary of time with black holes and so on. But here we're saying that there is an always present, before anything else happens, boundary of time. harmonically always syncing those small blue circles within the domain. They're all under one resonance, lined up in one plane, right? And there's other actions lined up that are balancing against this whole thing. And those other actions are the other measures. They're not the time, they're the space, but it's connected to time. It's not space, but it's charged, but it's connected to the other ones, right? They're all completely connected in a very geometrically definable way, and also a visual way. We can make a 3D model of this if I was really good at making animations, right? You could literally make a 3D model where you could let the viewer fly through, see all the different swirls of motion and so on, freeze it, point and say, this one here is this geometry, draw the circle, define it exactly. You could define them all. Once you define all the actions in this balance, it turns out, so far in the story, we've only shown that the time boundary is confirmed or is picked out, right? But all of these actions give us the 5 unique actions give us 5 unique boundaries that are the 5 Planck constants actually capping our physical reality. What's more than that, though, is that those boundary conditions have intersections. You can take this boundary and this one. In fact, all of those boundaries have specific ways they intersect in this balance action. They continue to always run into each other the same way, right? So those intersections now, not just the boundary condition, but the intersection of the boundary conditions define, even mathematically, the constants of nature. All of them. If you just list all the intersections, it spits out the constants of nature.
Oh, that's what you were talking about.
That kind of makes sense?
Yes.
So the constants of nature are the programmed tendencies of reality that we have measured. They literally characterize, to the best of our knowledge, the best of our measured ability, the actual characteristics of nature. The constants of nature and the particle zoo list the actual properties to the precision of our best investigation so far of what we know about reality. But they stand as a list of numbers. That's all we know. We know they have that measure. Don't know why. But we just invented a universe, and the simplest possible universe we could think of. We weren't even trying to make our universe, we were just trying to make a universe. The simplest universe we could come up with already intrinsically was programmed with the exact actions of our universe. All the constants of nature and all the division properties that single out the particles of matter we find. Because its boundary conditions happen to be exactly the boundary conditions of time, space, charge, mass, and temperature.
This is so deep, so simple, yet
it is simple enough that you can kind of see what I'm saying. Right?
I can kind of, because I feel like I'm one of those people, I need to sit there. It would take me a lot more time for me to digest all this information. But a huge part of me is just like, yeah, it's simple.
It seems
so simple, but I'm just like, holy, there's so much I don't understand.
I know a lot of people haven't tried doing personal investigation where they crunch in numbers and test things and do experiments on their own, so they have a familiarity with how difficult it is to explain something with an accuracy out to 2 significant digits, or 3, or 4, right? The best we've made in science, it makes a really good comparison, with all the best tools we have at CERN and so on, okay? The best we've ever done as humanity is get to 14. 14 significant digits is the most accurate measurement we've ever made of anything of any kind.
Wow.
So if you could explain something to 14 significant digit accuracy, you've explained something to the highest level we've been able to measure of anything. Any observation we've ever made of any kind. That's the level. So 14 is a big number to make it to, right? But I'd be happy to have an explanation that, honestly, compared to no explanation, if you give me something that got first 2 significant digits, I'd be like, okay, that's better than no explanation. This explanation gets us all 14 and predicts from there out as far as we want for all the constants in nature and all the masses. It doesn't miss a single note.
Mind blown.
Yeah, it's awesome.
This is good stuff. And this is like the first copy you're saying that you have of your book. I am excited for ordinary folks, but also people who actually understand mathematics and science and physics deeper than I can, so we can all help and really just teach each other.
Yeah, that's the whole
Like,
point. For
that's
all
it.
of us to elevate, right? The
Yeah.
exciting point about Einstein, this genius, come up with a new idea, is that someone had come up, it doesn't really matter who it is, that someone had come up with an idea that made sense of something no one's ever been able to make sense of before. Now, whether his idea
my
is
God.
right, ultimately, that didn't matter. It mattered that we had no options before, and now we have something that makes sense. That makes a big difference. Even if you ultimately supplant it with something that you think makes more sense, which hopefully we do, right? That's supposed to be the process.
Yeah.
This is a giant jump, because we're literally going from, we have spent all of this energy and been able to, with energy, get data points and collect a very precise description of how reality is constructed geometrically, right? That description is not in contest. It's right. Those are our data points. If you don't explain those, you're not explaining our measurements. That's a very precise description, but that description has no current understanding attached to it. No one, and I'm not attacking the idea. This is not anti-mainstream. It's no one's proposed an idea that makes sense of any of these parameters. No one's ever proposed an idea that could mathematically explain or reproduce any of these numbers to any accuracy, ever. This one simple story does them all.
This is
That's
huge.
unbelievable.
This is
unbelievable. People are like, well, you're looking for verification. Do you not understand the standards of verification? This level of verification is so far beyond anything that's ever been verified ever in science. We verified the whole foundation of science, capturing all of its most mysterious numbers to every single... I mean, if you're just like, well, I'm looking for verification, you don't know what verification is. Those are the ultimate things to verify. Dear God. Reading it yourself is the verification you're supposed to go after.
Yes.
Some other smart person telling you that this is how it is and you didn't really understand the idea, what good does that do to follow that kind of thinking? You know, it's ridiculous. This is something you can self-verify. Every equation in this book is algebra, meaning it's not an attack in character. I'm just pointing out everybody that goes to high school learns some form of algebra. You do division, subtraction, addition, right? Multiplication. That's it. That's it. You don't need to know how to do calculus to do this, to verify it. You certainly would need to know how to do calculus to try to approach coming to it to begin with, but to verify a pattern, like if someone says, I have a puzzle, it's a really good puzzle, and for 100 years, nobody comes up with the answer. And then the person's like, okay, after 100 years, you open up and see what the answer is. You open the answer, and everyone's like, oh, duh! But it took 100 years, nobody knew, right?
Right.
So 100 years, no one could come up with the idea, right? No one could think of it on their own. But the moment the idea was laid out and you heard it, like, wasn't
like,
anyone
aha.
contested that it was an idea. It was obvious.
Right.
So what was the problem? What were they missing the whole time?
Uh-huh.
They all currently had the ability to understand the idea the moment it was presented to them. Why didn't they have the ability to come up with the idea? It's the big question, right?
Right.
This is what we all want to know. What's stopping me right now from making my next big step in understanding? Yeah.
Self-identification, staying into a space of selfishness, pride, a lot of like not feeling good enough, smart enough, holding yourself back through thought process when it's like, hey, you're granted that, why not use it for the better?
All of those feelings that lead to thoughts that swamp you with doubt and confusion and so on. I'm not trying to say that doubt doesn't have a role. Doubt always has a functional role, and it should always come into play at the end.
It is, it's beautiful.
Yeah, but the doubt shouldn't be the thing that you live in. Because if you do, then you're not exploring. You can't. You're stuck.
Exactly.
You're just dealing with shit as it comes instead of making things happen. Yeah.
I love that. I'm excited for this. I think in this life, it's all about all of us learning to become more one with ourselves, and fundamentally that's interchangeable with falling in love and becoming more one with each other.
Yeah. Understanding each other more.
Exactly.
Yeah. And when you understand yourself more and other people more, you implicitly offer people to become something better, right?
And
you're
more than what they
offering
can
more
ever
engagement because you offered more understanding. It means you already paid more attention and more honor to them to begin with instead of this constant ignoring.
And, oh man,
let's go eat.
This was good.